Okay, so yeah, you've seen this slide before. The metals are going to be the bottom left, really the left-hand part to bottom right-hand part of the periodic table. Everything in black here. The things in blue, we call that the staircase. Those are the metalloids. Those have like properties that are sometimes metals, sometimes non-metals. And then the right-hand, top right-hand part of the periodic table, just to the right of the metalloids, those are your non-metals. Okay? I'm not going to like explicitly ask you which, like, is that a metal or a non-metal, but we're going to get into like how do you name these compounds next class. And a lot of how we name things in chemistry is based upon, well, is that compound made of metals or is it made of non-metals? Okay. Let me get my cursor over here. Okay. So, going over these three different kinds of bonds, there is an ionic bond. An ionic bond is whenever you have a metal plus a non-metal coming together. Okay. A covalent bond, a covalent compound, will be made up of when you have a non-metal plus another non-metal. Got two non-metals coming together, we call that a covalent bond. Go ahead and add this to your notes. You also, if you had a metalloid, I'm going to type that in before I forget. So covalent is not, it's usually non-metal plus non-metal, or it could be a metalloid plus another non-metal. Do the bracket thing there. Metalloid plus another non-metal. Okay. And then if like that compound is only made up of metals, then we would say that's metallic. All right. Now, what like actually is happening in a bond is there's some bonds always involve the valence electrons. Remember, the valence electrons are the outermost electrons. So here there is only one valence electron in that atom. Okay. So in order to understand like how bonds work, you have to remember like, well, how many valence electrons would a certain element have? And it was organized by group, where group 1, they all have one valence electron. Group 2, they all have two valence electrons. Group 3, they have 3, 4, and so on. An exception would be helium here. Helium has two valence electrons. We good on this slide? All right, going over the first kind of bond, an ionic bond. Whenever I say ionic, I hope you think of ions. Ionic ions, and that should make sense to you because ionic bonds involve the formation of cations and anions. We learned about those in Unit 1, where a cation, like that T there, looks like a positive sign. Anion, the N, think negative. Cations are where they have a positive charge. They get a positive charge because they are losing electrons. Anions get that negative charge because they gain electrons. So what's going on in an ionic bond is you have a cation and an anion coming together. So if we look here, for example, we have two atoms. We have a metal atom and a non-metal atom. Ionic bonds, always a metal plus a non-metal. So here's your metal. Metals want to lose electrons. Now, briefly to remind you why metals want to lose electrons, let me, well, I'll leave that to the next slide. Metals want to lose electrons. This non-metal wants to gain this electron from the metal. And what happens if you lose an electron? You become a cation. This metal atom has a positive charge. And this non-metal that gained the electron, it becomes an anion with that negative charge. Opposites attract, so the positive and negative are attracted to one another, and we will call that a bond. They are held together pretty tightly. Okay? So ionic bond, there's a complete transferring of a valence electron. Or it could be multiple valence electrons. It doesn't have to be just one. Okay? I think, did you learn this in 8th grade? Hopefully. No. All right. Doesn't matter. Okay, so getting into why. So why exactly are ionic bonds made of a metal and a non-metal? So if we look at the Bohr model here, you have a sodium atom. So this sodium atom, it has one valence electron. So here's the valence electron for sodium. And chlorine has 1, 2, 3, 4, 5, 6, 7 valence electrons. Atoms are the most stable when they have a full valence shell of electrons. Atoms are the most stable when that outside shell of electrons is completely full. So the metal atoms want to lose electrons, because if you're sodium and you get rid of that electron, then if you look at this sodium atom now this sodium atom's going to have a full second shell of electrons and it'll be stable. Chlorine and your nonmetals are the opposite scenario. This chlorine atom, if it can gain just one more electron, this electron here from sodium, then it'll have a full third shell of electrons. Okay, so that's why ionic bonds are between a metal and a non-metal atoms. They complement each other. Metals lose the electrons, the non-metals gain those electrons, and then they're both stable. The metal becoming the cation, the non-metal becoming the anion. So that, at least this concept here, that's a review from, really like Unit 3. We went over like the periodic table and the trends and stuff. Are we good? Got a question? Okay. Here's showing the ionic bond in kind of a little more detail. Not even really more detail, just kind of another slide going over it, and then introduces this idea of a formula unit. So a formula unit, this is like whenever you have, so say you have like a big thing of salt. And when I say salt, like sodium chloride salt, like table salt, NaCl. You have this big old thing of salt. That salt is actually held together in a crystal lattice structure where each Na and Cl, NaCl, NaCl, each unit of those we call a formula unit. In other words, in ionic bonds, we don't, we count them as formula units. In other words, like if I have a beaker of water, so you have this beaker of water here, and this is made of H2O. H2O, this is not going to be an ionic compound. How would you know that? Based on what I've told you so far, how would you know H2O is not an ionic compound? Carl, you got it?
Because it's not rigidly formed into a specific structure. Water is sort of fluid, and also the fact is that hydrogen and oxygen, they're nonmetals.
Perfect. This is hydrogen as a nonmetal. Oxygen's a nonmetal. So you would know this is a covalent compound. Yeah. And you're right. Kind of an emergent property from that is like these covalent compounds are typically going to be these liquids, whereas ionic compounds, because they're made of these cations and anions, they end up having this crystal lattice structure. That's why you have salt crystals. Any ionic compound, we call them salts. Okay. Anyways, so we can go through and we count each of these things, and you call that a formula unit. Whereas each individual H2O molecule in this beaker of water, we wouldn't call that a formula unit. We would just call that a molecule. You would say those are just molecules there. In other words, this slide's kind of more of like a technically kind of thing. Just if you hear the word formula units, just know we're referring to ionic compounds. We're counting ionic compounds here. Okay. Now, shifting gears a little bit, getting into covalent compounds. Covalent compounds are going to be between two nonmetals, or, caveat, two nonmetals, or metalloid plus a nonmetal. So go ahead and add that in there. Okay? So in a covalent bond, that means together. Like if you cooperate with someone, you're sharing the load. veil the valence electrons. So a covalent bond, there is an equal sharing of the valence electrons. So in other words, this isn't just like randomly named. The name makes sense based on what's happening with the valence electrons in this bond. So here's looking at some different kinds of covalent bonds. So here's water that we went over earlier, H2O. This oxygen and this hydrogen, they're sharing a pair. A pair of shoes has how many shoes? 2. So you'll say they're sharing 2 electrons or a pair of electrons. So you'll just kind of hear that phrase. Don't let that confuse you. This would technically be called a single bond or a single covalent bond, where you're sharing 1 pair or 2 electrons. Now you could have a double bond where you share 2 pairs of electrons. Or that'd be 4. And when we say electrons, we're talking about valence electrons, not just any old electron. You could have a triple bond where you're sharing 1, 2, 3 pairs of electrons. Okay? But notice how the electrons are being shared equally, more or less. Technically, like depending on the electronegativity, going back to Unit 3, the electronegativity of the element, these electrons are going to spin, like in carbon dioxide, oxygen is more electronegative than carbon. So technically, these electrons will spend more time around that oxygen atom than around the carbon. But overall, we would still say they're still sharing it. There's not a complete transfer of the electrons like you had in the ionic bond. Okay? Good here? Okay. Getting into metallic bonding. So metallic bonding is it's interesting. So metallic bonding, this is like, this is only metals here, right? So metallic bonding, this is when it's only metals coming together. So here we're looking at aluminum. So if you have a bunch of aluminum atoms coming together, there's this problem that arises because I said that atoms are the most stable when what happens?
They get a full cloud of electrons.
Yeah, a full cloud of electrons. Well, if you're aluminum has 1, 2, 3 valence electrons. So if you have a bunch of aluminum atoms trying to bond together, none of them wants electrons. So who's ever played like hot potato?
Yeah.
Or like, the idea of hot potato, right? Like if I throw a hot potato at you, the potato is so hot that like when one of you holds it, you can't hold it for very long. You're just going to like toss it to your neighbor, and it's going to keep going around and around just like that. That's metallic bonding. It's just this game of hot potato. The potato being the electrons, and then the people being the aluminum atoms. So take a look at it here. These are your electrons, and these electrons, they don't want to be near that aluminum atom. Doesn't want to hold on to the electrons, right? Because it wants to get rid of these electrons to get that full shell of electrons. So if you look at the second picture here, this aluminum atom, it's Al3+. This atom is stable because it lost those electrons. But again, the issue is if you have a whole thing of metal where all of these aluminum atoms are together, they are all just going to get rid of their electrons. And so you kind of have this like communal share of electrons, or like this hot potato game of electrons, where these electrons exist in this sea where they don't really belong to any one metal atom because nobody wants them. It's kind of sad if you think about it, Nobody wants the electrons here, It's like stray animals, maybe. All right, any questions about that? All right. So here's a slide summarizing everything for you. So you have ionic, which we call salts. So again, whenever you hear salt, you think of table salt. That's NaCl. But technically, anytime you have a metal and a non-metal together, we call that a salt. Covalent, 2 or more nonmetals. Remember, that could also be or a metalloid. And metallic, that's when it's only metals. Ionic bonds, how they form. The metals lose the ions, they become cations. Non-metals gain the electrons, forming the anions, and then opposites attract. Okay? Whereas in covalent bonds, there's an equal sharing of the electrons. Metallic bond, that's where it's the sea of electrons. This right here, where these electrons don't belong to any one atom. They're just kind of flowing around. Okay? A single unit, if it's an ionic compound, we would just call it a formula unit. You count think of this as like, how do you count these by? If you have a bunch of salts, you count them by formula units. If it's table salt, each formula unit would be NaCl, NaCl, NaCl. If it's like a beaker of water, something that's covalently bonded together, we just call it a molecule. Count them by individual water molecules, you would say. If it's metallic bonding, you count them by atoms. Because think about it. This is like a whole thing of copper. This would be a copper atom. That would be a copper atom. You would count them by individual copper atoms because there's not an actual bond like you would have here, and this would be methane. Like there's not a true like C to H, C to H, C to H that exists as one individual like Lego block. Okay. And here are some examples here. Remember, ionic compounds have that crystal lattice structure because of like the positive and negative charges coming together. It makes that like nice solid crystal. Okay. Nothing new on this slide. Just kind of another visual. Just sort of we haven't seen this picture here, but just showing you like all of them together here. So here's metallic bonding. Notice especially this cloud of valence electrons here that just are constantly being shared. All right, so now getting into the properties. So that's just kind of an overview of like what is an ionic bond, covalent bond, metallic. Now, what are the chemical properties that something that's made of ionic bonds or covalent bonds or metallic bonds have? Well, if we talk about electricity, if it is something that is made of ionic and covalent bonds, it does not conduct electricity. And that should make sense to you, right? Like, and well, that's really what you're going to explore here in this lab, partially, is if I give you an ionic compound, you'll see it should not conduct electricity. But if I give you something that's metallic, metals conduct electricity. That's how wires work, right? That should make some intuitive sense to you. Now, what hopefully you should appreciate now that you understand the model of metallic bonding is why do metals conduct electricity? It's because of the sea of electrons. So we talked about how if you have a sample of metal, like let's say this is a whole big block of copper, this copper is going to conduct electricity because each of these copper atoms forms an ion. It's going to form this ion here where they're going to get rid of their electrons. And these electrons, they exist as these communal, the sea of electrons. And what is electricity? The flow of electrons. So in metallic bonding, these electrons, because they don't belong to any one atom, that means these electrons are free to flow like the ocean, right? Like a sea. They can flow across this sample, and then we can utilize that to play Pokemon or like run electricity and stuff. See? I think that's kind of interesting, you know? Now, if you compare that to like a covalent bond here. Covalent bond, the electrons are tied down. Ionic bond, the electrons are tied down. That's why they don't pass the electricity. There's no movement of electrons. Okay, going on to our next property, brittle. If something is brittle, it shatters pretty easily. You know, in Texas, it doesn't like snow very often, and me and some friends were hanging out, right? And like, you know, we noticed like, oh my gosh, like there's this layer of ice on like the basketball hoop, and if you shot a basketball, you ever done this? Shot a basketball at the basketball hoop, and if there's like a layer of ice on the plastic basketball hoop, it'll like shatter. And we're like, oh, that's cool. And we noticed like his dad's car, like, oh my gosh, there's this layer of ice on his dad's car. It's like, oh, you can like shatter the ice and it like crumbles down. It's funny. And so we did that, and what happened?
The car exploded.
Yeah. I didn't do it, but one of my friends, he broke all of the windows in the car. His dad was so pissed. Like, I've never seen this man like be like his dad. His dad was like the gentle giant, and he's like 6'6", like comes out and was like, "What are you boys?" You know, like just all the window. And he explained to us, like literally explained to us, brittle. That is how I learned about brittle. If something is brittle, it shatters easily. So glass is an ionic compound where it shatters easily. What happens is, in glass or any sort of ionic compound, you have your cations and your anions. You have the positive and negative charges, and these are very rigid. They're held together super strongly. But what that means is, if I were to apply like a force, like lateral especially, that will then it's not flexible. Think of a liquid. Think of a water bed. You can bring back some water. You lay on a water bed, right? That water, it's made of these covalent bonds. It can shift a little bit easier than an ionic bond where if you apply a force, it just shatters or it just like shifts over and it can then crack. That substance can crack. That's how like salt crystals crack. So ionic compounds are brittle. Ionic and covalent. Ionic is the most brittle, is what I really want to say. Ionic is the most brittle. Ionic will crack the easiest. Covalent compounds, there's different degrees of like brittleness. We would still, like if you had to say yes or no, we would still say for our purposes covalent bonds are brittle. But you know, it can depend a little bit, especially on the state of matter and stuff and something and such, right? If it's like water really wouldn't be brittle because it's a liquid and it can shift. Okay. Looking at metallic bonds. Metallic bonds are not brittle. So going back to that car example, notice how we focus on the window shattering. I didn't say that the entire car shattered, like the metal frame of the car shattered, thankfully, because metals are not brittle. If you have something that's made of metallic bonds, like your metals, they aren't brittle. Like if I were to hit that car with a hammer, it's just going to shift. Now, let's put our phones up, please. Thank you. You hit that, think of swords. This is why, or this metal hammer. Like, you hit something, you take a metal hammer and you hit a metallic, some other metal, that metal doesn't just like shatter. And the reason is that sea of electrons. That sea of electrons will give metals the ability to bend and you can change the shape. That's why, okay, here's like a sheet of copper, right? Like this isn't just shattering as I'm bending it. This is made of metallic bonds. It's got this sea of electrons. It's malleable. I can bend it around and it'll still more or less retain its shape. Okay, so that's brittle. You get here? Electrolytes. Think of like Gatorade. What is the idea of drinking Gatorade? Electrolyte. And why do you want electrolytes? So what? Energy, sort of. What might happen if you don't drink Gatorade, or at least you don't have enough water? What would happen in like a sports game? You would dehydrate. And what happens if you dehydrate? You die. Before you dehydrate and die, something else is going to happen if you're playing sports. It's like it's not like the two extremes. First you get really tired, and at some point you get too dizzy and you pass out. Those would all happen. I mean, have you all never experienced these? You ever woken up in the middle of the night, grabbing your leg? Yeah, Jaden, go ahead. Cramp. You will start cramping. The idea here is your body, your nervous system is made of electricity. I don't know if you thought it. Like you run electricity through your brain and through your body. Electricity depends on these ions. Where do ions come from? Ionic compounds. So if you look at Gatorade has a lot of salts. So, here they're showing KCl, but it could be NaCl. Anyways, you put salts in water. So if you take a salt crystal by itself, it won't conduct electricity. But if you put salts in water, those salts will break apart into the ions. And if you break this apart into the ions, you have these electrons. You have these free electrons in the solution of water, and then that will conduct electricity. So that's the idea of drinking some sort of electrolyte solution, is you're basically like getting these free electrons that you can use to like keep running your nervous system. It's the idea behind batteries, right? Batteries are going to be made of an electrolyte solution where you're going to have some sort of ionic compound, like a lithium-ion batteries, right? You're using ions from a lithium, and then it could be, I don't know what the anion would be. Lithium would be the cation, but anyways, I don't make batteries, but the basic idea of a battery is you have an electrolyte solution, and you're utilizing that freeing of electrons from the water dissolving the salts. Okay? Okay. We good here? This is saying that, why do salts dissolve in water? Well, oxygen has a slight negative charge, hydrogen has a slight positive charge, coming about because of the electronegativities that we talked about in Unit 3. So here, this is chlorine. Chlorine's got that negative charge, so it's going to be attracted to the slight positive charge from hydrogen. And then potassium, it's got that positive charge, so it's attracted to the slight negative charge of the oxygen molecule. That's why ionic compounds will dissolve in water. If you have covalent compounds, you don't get these true positive and negative. You don't get those ions, so the water can't completely dissolve that thing. Okay. All right. So looking at bonds. So I mentioned the word electronegativity. Talked about electronegativity in Unit 3. Electronegativity, that is how badly an atom wants electrons. How badly atom wants electrons. So if you have a bond where you have atoms being some sort of sharing of electrons, you could have a covalent bond that we would say is nonpolar, where there is an equal sharing of electrons. So if you look at the atoms, they have the same electronegativity, meaning they share the electrons equally. That's what this is trying to show. This is trying to show like this would be that'd be an atom, that's an atom. This would be like the nucleus, that's the nucleus, and the electrons are being shared equally. Whereas if you have a polar covalent bond, you have an unequal sharing of electrons. So let's say this is an oxygen atom, that's a hydrogen atom. The oxygen atom is more electronegative than the oxygen, so the electrons spend more time around the oxygen. The hydrogen has a slight positive charge because the electrons are spending their time around the oxygen. Okay? And then an ionic bond, you have a complete transferring of the electrons. So ionic bonds have the biggest difference in electronegativity. So here the electrons got completely transferred to, let's say, Cl, and that would be like Na. Chlorine has a way higher electronegativity than sodium. That's why it's going to have the highest electronegativity difference. Now metallic bonds, because it's a bond with the exact same atom, like it's just a bunch of, like, say, copper atoms together, copper is going to have these two copper atoms would all have the exact same electronegativity. So the difference between the two of them would be a 0 for electronegativity difference. Okay. We'll talk a lot more about like polar and non-polar covalent bonds a little bit later on, but more just kind of introducing that idea of electronegativity difference. All right, getting to the end, looking at melting point. So melting point is exactly what it sounds like. What is the point, or what is the temperature that something will melt at? So if you are an ionic or a metallic molecule, something made of ionic and metallic bonds, you're going to have a very high melting point. You would have to raise the temperature really, really high to dissolve that thing. And the reason for that is the strength of the bonds that holds it together. And ionic bonds are super, super strong. So it would take a lot of energy, a high temperature, to break apart those bonds. Same with the metallic bond. Okay. Whereas covalent bonds, covalent molecules, their bonds are going to be a little bit weaker. So I wouldn't have to raise the temperature as high to dissolve the covalent molecules, to dissolve those covalent bonds. So ice cream held together by covalent bonds. That's why it's going to melt pretty easily. You got to get ice cream made of metallic bonds. That's don't do that. Anyways, okay. I'm not going to read this chart to you. This is just like one chart that summarizes everything. Okay, so just kind of all the properties, and then yes or no for the different ionic, covalent, or metallic bonds. And I think that's it. Okay, so let me show you the lab here. What you're doing with the lab. Let me stop this.